So as I mentioned in the title, I'm going to talk about the basics. So for those of you who are very familiar with MRI, I'm not going to tell you anything new. Interaction between magnetic field and nuclei are still the same. But for those who are not familiar, I think it's interesting to try to understand what is going on when we do imaging. And before doing imaging, maybe we need to understand what is spectroscopy, because spectroscopy is, you cannot understand, in my opinion, you cannot understand imaging if you don't understand spectroscopy. So to start with, you know, in the field of MRI, you've got multiple Nobel Prizes, you know, which are here. So starting from the last one, you know, these two guys, you know, have actually invented MRI and kind of a fast MRI, and they get the Nobel Prize not so far ago, no, 2023, something like 20 years ago. And starting from here, you know, this guy was doing some chemistry, so he did some research about the properties of nuclei, and we are going to talk about the properties of nuclei to understand magnetic resonance imaging. You've got these two guys, very famous, Bloch and Purcell. They did all the equations related to physics of MRI. So if you are familiar with MRI, you are using this kind of equations to understand the signal. Ernst, there is a very famous formula related to him, related to the flip angle during a spectroscopic experiment. So he's a chemist, and I've already talked about these two guys. So we are going to talk about NMR, nuclear magnetic resonance, which is a physical technique. And with this technique, you can do two different things. You can do what I've mentioned before, spectroscopy. So spectroscopy is very simple, you know, it's kind of chemical analysis of any tissue, can be in vivo, can be ex vivo. And so you can also do imaging, but imaging is a little bit more, at least to me, more sophisticated, because you need more a different approach to do imaging. And imaging spectroscopy are not exactly the same. So a spectrum coming from the experiment, it looks like this, you know. You've got a kind of, I would say, chemical information of the tissue you are looking at. So in that particular case, this is the phosphorylated metabolites. So it means that all the compounds which are with phosphorus, because phosphorus is something we can look at with spectroscopy. And of course, you can also do imaging, as I said. And so here, it is not imaging of phosphorus, it's the imaging of protons. So imaging is just a matter of looking at water and fat mainly. Whatever the organ, it will be mainly water and fat. And this is an image of a thigh, you know, an axial slice of the thigh. And so everything which is white is fat, and everything which is gray is muscle. And of course, black is nothing. And you can also, of course, do spectroscopy of proton if you want, and depending on the organ, it can be interesting or not. So of course, you are very familiar with this. This is maybe 90% of the application of MRI. This is MRI of brain, but still, even if brain, you don't see much than water and fat, okay, and maybe some liquid, but it will be related to fat. And if you want to do spectroscopy, of course, you can also do spectroscopy of brain. And in here, it's not phosphorus spectroscopy, but is proton spectroscopy. And in here, you don't see water and fat, because for the metabolism, it's not so interesting to look at water and fat. So you are going to look at all the metabolites with protons. You have lactate, choline, creatine. But in order to do that, you need to eliminate the signal of water, because signal of water is so big that you wouldn't see this metabolite if you don't suppress the signal from water. So having said that, maybe we need to understand what is in these words nuclear magnetic resonance. When you talk about nuclei, we are not talking about all sorts of nuclei. We're talking about specific type of nuclei. And they are those with a non-zero magnetic spin. So it means they've got these physical properties called spin. So if the nucleus doesn't have a spin, you won't be able to detect it for the NMR. Whether it would be imaging or spectroscopy, it doesn't matter, but you wouldn't see it. So the question, are all the nuclei observable? I already gave you the answer. The answer is no. And so maybe number one will be a proton, because as I've shown you, when you do imaging of proton from water and fat. But there are some other nuclei which are of interest, maybe not to do imaging, maybe more for spectroscopy, unless some of them are of interest for imaging. So I've got a list in here. So I've mentioned the proton already. You got C13, this is carbon 13. So you can do some imaging with that. You got 31 phosphorus. I've already mentioned this. This is mainly for the studies dedicated to energy metabolism. You've got nitrogen 14. Maybe I didn't mention here, but I should have done it. You've got sodium 23, which is quite of interest for imaging. And yeah, I didn't mention that for C13, it's mainly related to spectroscopy, and people are looking at the glycogen within the muscle using this. Okay, so glycogen, you know what it is. It is a kind of the pool of sugar inside the muscle. It can be inside the liver as well, and you can do NMR spectroscopy of C13 to follow the changes in glycogen if you want. It's not easy, but this is possible. So, and as I said, that if you don't have a spin, you won't be able to be sensitive to NMR. And these two, C12, which is the most abundant isotope in our body, we are not able to see it. And oxygen 16 is the same. We are not able to see it because, they don't have the physical property needed to be observable with NMR. Magnetic, of course, we are talking about magnetic field. And the specificity of this magnetic field is very, very high. Okay, so you all know that we've got a magnetic field on Earth, which is 6 to 10 to the minus 5 Tesla, because the unit is Tesla, so very small. But we are not using this kind of field in MRI or in MR spectroscopy. We are using this kind of field in here from 1.5 to 11, even now more than that. Okay, so 11 Tesla, if you compare with the value of the Earth magnetic field, you can understand that this is very, very huge. And the question is, how can we generate this kind of field? Maybe you remember that if you want to generate a magnetic field, you just have to have a current flowing through a wire. You will generate a magnetic field. Okay, this is something you learn at school. But what is the intensity of the kind of field you can generate with this is not 1.5 Tesla or even less 10 Tesla. Because if you are doing this kind of device, you'll be limited by something. Do you know what is limiting the production of the field in this case? Because you are going to hit the wire and you're not able to go further than less than half of a Tesla. Okay, so of course you've got permanent magnet, you don't need this. You've got the electrical magnet, which is this kind of device, so you'll be producing half of a Tesla. But if you want to produce more, then you won't be able to do it with this. So you need what we call the superconducting magnet. And maybe I'll tell you very briefly what is superconductivity. It means that actually you are going just to cancel the resistance of the wire to the electrical current. So it means that if the resistance is 0, then you can produce a very high magnetic field, and this is what people have been doing over the last century. So you can see in here the resistance at a given temperature. Yeah, I forget to say that you will lose the resistance if you if you put this kind of metal at very low temperature. So very low means the temperature kind of absolute zero. And then if you are able to do it, you will take the resistance to zero, and then you will be able to produce a very high magnetic field. And this is what people are using, you know, for the clinical systems. They are using this kind of thing. And so here you've got a schematic of different metals that have been used and the temperature related to those metals. And for now, people are mainly using this kind of mixture to produce the superconducting magnet which are generating this very high magnetic field. Then resonance. Resonance more or less means that, you know, we are talking about the interaction between the magnetic field and the nuclei, and you are going to talk about some transition between different energy states for this nuclei of interest. So I'm going to tell you a little bit more in the next slide. So this looks very simple, you know. So you've got the magnetic field in here, which is going higher, and you've got the energy states in here. So what we need to understand is that if there is no magnetic field, you know, all the nuclei, we cannot talk about any different energy states. But if you are going to put a magnetic field, or we call it B0, so you are going to create, you know, different energy states which are located in here. And what you can see in here is that if you increase the value of the magnetic field, the energy difference between the states is going to go up. And I'm going to show you that this is very important. This explains to you why people are trying to go in the higher and higher field. You know, the only reason is to increase this energy gap between the two states, and you will understand why we need to have such a very high gap. So we are here in the very simple situation where you've got only two energy states, and it depends on the properties of the nuclei. So this is the case for proton. It won't be the case for another nucleus, for instance, but just to understand very simply, we will talk about just two energy states. Yeah, here you've got, you know, the experimental curve related the SNR, the signal-to-noise ratio, maybe the quality of the signal if you want, or the intensity related to the magnetic field, and you can see that, you know, it can go very high with the increasing magnetic field, and so that's why, you know, people want to be here if they want to assess different sort of Liebing phenomenon. And this is, you know, something I've just picked up from the literature, of course, but from the very high field magnetic magnet which has been built in Paris. And you can see the difference in here between 3 Tesla, 7 Tesla, and the one they've got 11.7 Tesla. So with this kind of field, you know, you can dramatically increase the resolution, or you can increase the acquisition, or decrease the acquisition time. And what the clinician is saying now is that, you know, with the 7 Tesla coming to the clinical field, they are seeing structures that were invisible before. So they need to relearn, you know, how to look at the images, because, you know, for them, the first images at 7 Tesla were full of abnormalities. So now they need to re-understand what is the new contrast at 7 Tesla, and it will be probably the same for 11.7 Tesla when they will replace the 7 Tesla, maybe in decades. But just to let you know that it's not so simple, you know, to go from one field to another, because the images can be very, very different. Okay, so to make it clear and simple, NMR is, as it is mentioned in here, a phenomenon when you put the nuclei, we talked about the nuclei before, you know, not all of them, but some of them, in a static magnetic field. So we already explained that this static magnetic field is going to be 1.5 or 10 Tesla, whatever. But it's not enough. We then need to put this entire system to a second magnetic field, which is not going to be static, but it's going to be oscillating. Okay, so imagine you have three characters in the story. You've got the nuclei with a physical property. You've got the static magnetic field, which we call B0, and we've got a second magnetic field, which we call B1. If we've got all the three, you're ready to do the experiment. And now we are going to try to understand what we do with all these fields. So I told you that the nuclei need to have magnetic properties, which we call spin. So spin more or less can be understood as a kind of oscillation of the nuclei of interest. So it's a kind of polarized structure, if you want. And then if you send a magnetic field on this oscillating nuclei, then you are going to do one thing which is very specific. You are going to more or less make it spin in a unique, predictable way. So the way is actually a frequency. You are going to impose a frequency of oscillation to the nuclei of interest due to this strong magnetic field. And then, but this is not the NMR phenomenon, not yet. Okay, if you want to recall the NMR phenomenon, you need to wait. So the nuclei are going to give you back some energy, and you are going to measure this energy. This energy is actually another oscillating magnetic field. And then if you've got a proper device, which we call antenna, then you can record the signal, which will be a spectrum or an image, depending on what the kind of experiment you are going to do. Okay, so the coils, what are they looking like? So the coil will be actually adapted to the organs you want to scan. So I'm mainly showing coils for muscle because I'm doing muscle investigations. But of course, you've got coils for all the parts of the body. You've got coil for the wrist, coil for the knee, coil for the head. And each time there will be specific, to kind of optimize the magnetic field within the region of interest, and also to optimize the reception of the signal. So I've shown two different in here. This one is a kind of coil producing an homogeneous B1, and the other one, this one, which we call surface coil, which is a little bit different. It won't produce an homogeneous B1 field, but I'm not going to enter into the detail of that. So coming back to our spins, so I said, okay, they are rotating, and so we can assimilate them as a kind of polarized structure. And so if we put this polarized structure, well, before putting the polarized structure in the magnetic field, the orientation of the different nuclei in here is kind of random. So you don't have an organized structure, if you want. But when you are going to put them in the magnetic field, the very strong magnetic field I was talking about before, then they are going to align according to, in this example, will be two different states. Why two? Because we are talking about proton. The spin number of proton is 1/2, and the number of direction you can have is 2 times the spin number plus 1. So it will be, in that case, it will be 2. But as I said before, if you've got another nucleus with a spin number which is different than 1/2, then the situation will be completely different, and I won't be able to explain this as easily as I can explain with this. So we put the nuclei in the magnetic field, so they are going to align according to the field or opposite to the field. And as you can see in this schematic drawing in here, you've got a little bit more in one situation than the other. And this is very, very important, This is the basic, actually, of the MR signal. If you wouldn't have this difference, you wouldn't be able to get any signal. Okay, so and in addition to have this different orientation, the spins are going to process around the direction of the magnetic field, with a given frequency. This is what it is drawn in here, So imagine, so this is just for one, but you can imagine that some of them will be processing that way, and some of them will be processing in the other plane in here, and you've got all the millions of nuclei who are processing when they are in the magnetic field. And if there is only one formula you need to know, is this one, no more than that. The frequency of this precession, omega 0 in here, is directly proportional to B0. B0 is the magnetic field, you remember? And with a ratio in here, which is called the Garreau magnetic ratio, which is specific for each type of nucleus. So proton will be a given ratio, phosphorus will have another one, carbon will have another one, okay? And so it means that if you are if you are a proton inside the molecule, the frequency can be calculating you this. And if you change this, the precession frequency is going to change, of course. So if we go, if we move ahead, so it's always the same thing, two types of nuclei, some of them in one state, some of them in another state, but the number of nuclei will be different. And if we want to know how much do we have in one state and how much we have in the other state, we need to know this equilibrium of Boltzmann, and which very simply gives you the ratio between the number of nuclei in one state and the number of nuclei in the other one. And as I mentioned before, we need to have a difference, otherwise you won't have the NMR signal. And you can see in here, this is of course related to the energy difference between the two states, which is going to change according to the magnetic field. If you are here, it will be smaller than here. And it will be also related to the temperature. If you change the temperature, you are going to change this equilibrium. So now, if we really want to know how much is the difference, so I took the Boltzmann equilibrium and did a very simple calculation. Imagine you've got 2 million of nuclei, and more or less you will be half and half at the first glance. So you mean that this will be the total, and this will be the number of nuclei in the first state and the number of nuclei in the second state. So actually, you cannot distinguish them because the numbers are very close. So what I did, I changed the scale, and so you can have the figure I've shown you before with so the number of nuclei in one state and the number of nuclei in another state according to the magnetic field. But if you look at the numbers in here, the difference is very, very small. You imagine that we've got 2 million of nuclei, and you can see the number. The difference is something like 50 or 10. It's nothing, okay? And if you calculate the ratio between those two, so the number is a few hundred of % here. Is nothing. It means what? It means that the difference between the two levels in terms of amount of nuclei is very small, and it explains why this technique NMR is very poorly sensitive. It's not a very sensitive technique, We are able to get very nice images just for one reason, is that we've got millions of nuclei, millions of molecules of water, for instance. Okay, so that's why you've got nice images. But for instance, if you change the nuclei, let's go to phosphorus, for instance, you've got much less molecule of phosphorus than molecule of water in the body. So it would be very difficult to get some images of phosphorus. And you won't be able to have all the anatomical details you can have on an image of a brain, for instance. It's just because the amount of water molecule is very small, is very high, sorry. But still the difference is very small. And if you go back to this, you can see that, okay, if you go higher in the value of magnetic field, the difference is going to be higher. And so the sensitivity of the technique is going to increase. Okay, so that's why at 11 Tesla, you've got such a resolution, because you are talking with more nuclei than you were talking with when you were using a smaller magnetic field. Okay, so now the question is, okay, so I've got the nuclei, I've got the main magnetic field B0, which can be more or less large, but then I need to do something to get the NMR signal, because so far I've got nothing. Okay, so what I need to do, I need to provide to the system a certain amount of energy so that the nuclei which are in one state, or some of them, are going to move to the other state. Okay, and what we are looking for is to kind of get the two localization equal in intensity. Okay, so we want to have, so you remember that we've got some more nuclei in this state, so we need to take this small amount and put it in here, but for that we need to provide this energy. Okay, and this energy will be the second magnetic field I was talking about, this oscillating magnetic field, which will have a given frequency. And you can imagine that the frequency you are going to give is the precession frequency of the spin I was talking about before. This omega 0 is gamma B0. This is the frequency you are going to give. So this is the energy you are going to provide. So I'm not going to talk about the constant. And so you can go back to this formula I gave you before. So the frequency, the energy you need to give is going to provide the same frequency as the one the nuclei are rotating around the B0. Okay, so this is not so interesting, but just to say that this energy is actually part of the radio frequencies, in terms of energy. So it means that it's not very high energy. If you look at the different imaging techniques in here, you've got gamma, X-ray, and here you've got NMR. You can see the energy is very low, and that's why we are saying that NMR is non-invasive. We can repeat the NMR experiment several times, it's okay, but you cannot do several X-rays, in the same days or every day, because it will be harmful. So NMR is not aggressive, but is not sensitive. So you need to deal with that. Okay, so this was simple, just two, but actually you've got millions of them, and you can imagine that some of them are aligned in one direction, and some of them are aligned in the other direction. So in order to understand that, we're going to sum all of them, and so you'll be like this. If you got this this frame, with the three orthogonal axes, you've got the more or less the spin, which are either in one direction or another one, and you can also imagine that they are rotating around Z in here. Okay, so if you do the sum of all of that, as we know that they are a little bit more in this direction, if you do the sum, of course, the macroscopist vector will have only one direction, will be only this one. And so we are talking about the magnetization along the Z axis, and we call it MZ. Okay, and so of course it's still rotating, but for the matter of simplification, we are not going to have it rotating. It will be stable like this. Okay, So this is a kind of summary of all of that, and also with the formula of the magnetization in here, which is related to B0, temperature, and a lot of different constants. And so you can see that here you've got the random orientation. When you've got the B0, the orientation is going to be different. So you are going to create a magnetization along the z-axis in here, which was not there before without the B0. And then you can imagine that, okay, you've got the macroscopic vector rotating around B0. Okay, so now we don't have the NMR signal. Okay, we have created a kind of magnetization along the z-axis, but we don't have the signal. So as I said before, if we want to get the signal, we need to add this energy E related to the frequency of precession, and then you will be able to do this. You are going to tilt the magnetization away from the z-axis, because this is where you are going to be able to measure it. Okay? And so the question will be, how can we flip this magnetization from here to here? So if you imagine, you add different spins aligned in one direction and in the other direction, okay? And they are all rotating around the z-axis, okay? If I provide this energy E, okay, you are going to have exactly the same number of nuclei processing in one direction and the other directions, okay? So if you have exactly the same number in here, and they are all rotating around, okay? So you need to imagine what is the projection of this kind of magnetization in the axial plane, and what is the value of the magnetization in the z-axis, okay? So projection in the z-axis, if you've got the same number of nuclei in this state and in this state, if you do the projection like this, you're going to actually get this magnetization to 0. Okay, so this is what we need to understand. If you go from B0 to B0 plus the famous B1, the magnetization along the z-axis is going to go to 0. Okay? And then if you think about the projection in this direction, you know, in this plane in here, okay, you're going to create a new magnetization in here, which was not existing before, you know, you didn't have any magnetization in here. And so that's why at this stage, when you put the B1, you create this magnetization, which we're going to call MXY, if you want. Okay, so with B0, you've got the magnetization Z, and if you put B0 plus B1, this is going to go to B0 to 0, and this is going to go to a value which was 0 before. Okay?
Sorry, I probably missed the point. But if there's the same number of nuclei that are upward spin, downward spin, then M0 should be 0.
It is 0 in that situation, but not here.
Why not?
Because when you put B0, you don't have the same number. You don't. Yeah. When you put B0, you just create a difference, and the difference is not going to be 0, and that's why you got MZ. But if you put on the top of B0, you put B1, you put this energy in here, then you're going to have the number equal, and that's why this is going to go to 0, and this is going to go.
What remains then is the component which is not axial.
Exactly. And here it was 0, and here is not 0. But in order to that, you need to understand that, or maybe I will explain it later. But it's not so obvious that this is going to be created, you know, because this, what I said to you, if you can do the projection and do the sum, this is true only if the frequency of precession is always the same for all of them. but it is not true. I will tell you afterwards, but keep in mind that in order to that, you need to have the precession, the frequency precession, which is the same for all the protons, if you want. Okay? I will go back to do this a little bit later. Yeah.
I didn't get how this U1 is oriented. I didn't understand.
Okay. Maybe. Oh, can I write here or not? Okay, so you've got you are in this frame in here, and you've got, let's say, you've got the spin which are like this, right? And this is true if you've got B0, but if you don't have B0, you will be, you know, randomly okay. Then, if you so this is with B0, and if you put B0, which is the static magnetic field, plus the B1, which is this one, I told you that this is an oscillating magnetic field with a given frequency, which is equal to the frequency of precession of this spin in here, because, you know, the situation is not static in here. You need to imagine that the spin are going around like this, okay? So if you, if you are in this situation, if you take the macroscopic value of this, it will be like this. This is what we call MZ, okay? But here you've got nothing, right? You've got nothing. Why? Because, you know, the sum will be 0. In this axial plane, the sum will be 0. If you put B1, what you are going to do, you are going to equalize the different levels. So it means that here you will have 2, and here you have 2 as well. Okay? And they are still rotating around, like this. Okay? Then, the sum you did before, which was not 0, because, you know, you have more in here than in here. So if you do the sum in here on this axis, it'll go to 0. Okay? Because you have here, it will be 0. But now, if you do the projection in here, it won't be 0. It was 0 before, but it's not going to be 0 here. This is a little bit tricky, but because actually I'm not saying all the things, because with this formula, you know, nu equal gamma B0, if you take this as the truth, you have actually only one frequency for all the protons, for instance, all the phosphorus or all whatever. Okay? So it means that in here, they are all rotating, they will be rotating in the same, at the same frequency. But it is not true. This is not true. Why? Because, you know, these protons are part of different molecules. You know, I'm talking about water, so very simple in here. So you've got the proton in the water molecule is in here. But we are talking also about fat, okay? Fat is completely different. Fat is this. You know, a lot of carbon and proton. Okay? And in fact, the frequency, the precession frequency, is going to be related to this, but also to the electronic environment of the protons in here. So it means that the proton of fat are not going to have the same precession as the proton of water, because you can see very easily that the electronic environment is not the same. Okay? So I'm just telling you that because, in fact, you know, you've got here different spins, and you can imagine that the frequency is different. But if you want to get a magnetization on this axis in here, you not only need to equalize the two populations, but you also need to have a single frequency of precession, not multiple frequencies. And so this B1 is going to do that. It's going to do two things. It's going to equalize the population, okay? But also is going to make the frequency with a single value only, okay? Because otherwise, if you've got, different frequencies in here, you would not create the magnetization in this axis in here. So this is the second kind of effect of this B1, okay? And so that's why the main message is that, before, without the B1, just the B0, you didn't get a value of in this axis in here. If you put B1 on the top of B0, then you're going to create this magnetization in here. And this is this magnetization that you're going to record to get the NMR signal. Because so far, I didn't talk about any signal, For now, until now, we have nothing. Okay, we need to actually wait what we call the relaxation. So relaxation means that you are going to suppress the B1, so you're going to go back in here. So just the opposite, you're going to have different numbers of nuclei in the different, but it's going to change with time. And this is this change that you are going to record. And this is here. So relaxation is quite sophisticated, remember that, okay, no, this is not relaxation, but it can look like this. Sorry. Yeah, this is what I mentioned. No, in here, this is a kind of summary. In here, B0, you've got MZ is not 0, and MXY is 0. And then if you put B1, you're going to have MZ is going to go to 0, and this value of magnetization is going to appear, more or less. Okay? And then, okay, this is a kind of summary as well. So B0 plus B1, you do this. And if you go back to B0, then you're going to back to the previous situation. And this is what you are going to record to collect the NMR signal. And this is what we call relaxation. So relaxation means that MXY is going to be back to 0, and MZ is going to be back to MZ. Okay? And it's like this, because you've got two types of relaxation. You've got one relaxation in the z-axis and one relaxation in the axial axis. And this is kind of conditioned by two relaxation processes, what we call T1 and T2. T1 relaxation and T2 relaxation. It means that T2 will be the the phenomenon of going back, going from MXY to 0, and T1 will give you information about going from MZ is 0 to MZ is going to back to MZ. Okay, so it's a kind of more sophisticated process combining two things. And so you've got the equation on here. For the T1 relaxation, you go from 0 to the maximum value. And so this is very simple to understand. So you go in, so it means that on the image, you go from black to white. And if you go to the other relaxation process, which is conditioned by T2, this is the opposite. This is what I said. You start from MXY, which is not 0, and it's going to go to 0 with a different equation conditioned by T2. And so you can imagine, okay, T2 means that you get a certain amount of signal. And so in terms of contrast, on the T2 you go from black, you go from white to black on the image. Okay, but this is not interesting for now. So now if we give a summary of everything, okay, initially we've got MZ, which were here. Then we tilt the magnetization on the other axis, okay? And then we have the relaxation. So the relaxation means that the magnetization is going to turn around and go back to the initial value. So you have to follow the magnetization. You know, it's going to go around like this, in this axis in here, and also it's going to go back up in the z-axis. So you can follow it like this, you know. It goes like this, so negative value, then positive value, but a little bit up, and then you're going to continue, negative value, but smaller, and then positive value, a little bit smaller, and again, until, you know, you go back to here. And what you are going to measure is actually this. You are going to measure the phase and the intensity of this signal over time, and this is the NMR signal. Let's have a look. Okay, you've got the magnetization in here with respect to time, okay? And we're going to follow this step by step. So if we start with the initial phase, we've got this number in here. Then, okay, this is positive and quite high, so we put the number in here. Then it's going to go to negative, so on the other part of the graph, but the absolute value is a little bit smaller because, you know, the magnetization is going back. Then again positive, but a little bit smaller. Then again negative and a little bit smaller. And this is what you can draw if you link all the points in here. You know, up and down, and the intensity is going down. And this is the NMR signal in here. This is the change of the magnetization in the X-ray plane, okay, which is going from the maximum value to 0 according to this type of oscillation. And this is exactly the NMR signal, but it doesn't look at an image, and it doesn't look at as a spectrum, you know, and before I showed you spectrum and images, okay? So if you want to, you remember that the proton or any kind of nuclear are processing around Z at a given frequency. So this is what you are looking for. The information you are looking for is the frequency of precession of these different nuclei, okay? So once you've got the evolution of the signal according to time, you just have to do a Fourier transformation, and you're going to get the frequency component of this. And the frequency component will be, you imagine this is a signal like this, so you have the answer. You know, you've got two frequencies in here, so it means that you've got kind of two families of frequencies, so two families of proton. So it means that if you do a proton spectroscopy of any kind of organ, if you do the Fourier transformation of this, you'll get two signals, one related to water and one related to fat, mainly, okay? So this is kind of ideal sinusoidal signal. You do the Fourier transformation, you got one frequency, but in the real life, it looks like this, you know, because you've got multiple frequencies in the spectrum. So the idea is that you need to identify the frequencies, okay? But just do the Fourier transformation, and you will get this. This is not proton, it's phosphorus, but it will be the same. I put this because you've got a little bit more information. So what can you see in here? You can see, you can see different frequencies along, because this is the frequency now in here. And this is the intensity. So it means that in the tissue I'm scanning now, I've got 1, 2, 3, 4, 5 different components, so 5 different molecules, family of molecules with phosphorus, okay? And the quantity is here. So this one is very much concentrated, this one much less, and this one much less. Okay, so I've got the identity of the phosphorus nuclei which were in the sample when I was doing the scanning. Okay, and so they are having different frequencies in here, because as I said to you before, this is the same as here. because the electronic environment is different, okay? And so we know who is who. You know, we know who is this molecule in here, and we know who is this molecule in here. We know everything. Okay, initially we didn't know, but it's just that you have to guess and do some phantom scanning, and you can go back to here. And so as said, you can distinguish different molecules. Okay, imagine though molecule A with phosphorus and molecule B with phosphorus. You know, the electronic environment is different, so you can distinguish two molecules. But you can do even more than that, because you know these three molecules in these three frequencies in here are part of the same molecule. Okay, and this is what we call ATP. I don't know whether you know this molecule in here is adenosine 3-phosphate. This is something all the cells are using if they want to produce energy. And this molecule looks like this, you know, is phosphate, phosphate, and phosphate. You know, is called 3-phosphate because actually you've got 3-phosphate. And in this spectrum, you can see that you have three different frequencies for each phosphorus in here. Because of what? Because, you know, the electronic environment is different, so that spectroscopy is able to distinguish this one than this one. Okay, and it won't be the same position, it won't be the same identity in the spectrum in here. It will be the same if you do proton spectroscopy. Okay, you've got water is more or less always water, but fat, you've got different type of fat molecules. You know, you can have one like this, or you can have one with a double bond in here, and so the proton in here will have a different electronic environment. So you will have only not one frequency of fat on the spectrum, but more than one. Okay, you will have multiple fat peaks in the spectrum in here. Okay, yeah.
Sorry, still bothered by the B1, in the sense that you determine the energy essentially that you have to send in
Yes.
the system by knowing the difference between the upper branch and the lower branch.
Exactly.
But that depends on the particular electronic environment of a given nucleus.
Absolutely. Yes.
So,
Yeah.
so let's say that you send in the right energy
Yeah.
for water,
Yeah.
but it will not be the right energy for proton.
For fat, for instance. Yeah.
And so, so that means that actually the Z component
Yeah.
of the whole thing won't be
Yeah.
zero at the end.
Absolutely. You're right. If, you know, we were able to be selective enough to get only one frequency, but actually we are using frequency pulses that are actually exciting a kind of band, you know, and that's why with a single pulse, we are able to excite all the bandwidths. But you're right, if you were able to get only one selective excitation, we'll touch only the proton from water or only the proton for fat, but not both of them. And the fact that we are using a pulse, we are exciting everything at the same time. But what is interesting is that when you remove this, the frequency is going to go back to each value, and we will be able to distinguish the frequency of water and the frequency of fat, or the frequency of different phosphorus, as you can see in here. So if you understand this, you understand everything in terms of NMR, except that in here you are doing spectroscopy, so you've got the identity of the signals, you've got the intensity, but you know, if you want to, yeah, this is the thing, but we don't care. Yeah, you remember an image, you know, I showed you an image before. It doesn't look like a spectrum in here, and an image, you need to know that, for instance, you know, in the image of the thigh, you need to know that the bone is in the middle, or the fat is around. And in here, in this spectrum in here, I don't have this information about where is the water. Is it in the middle, or is it around the tissue I am scanning? So we don't have this information. This is something which is missing. And this is something which we need if you want to do imaging. Okay, donc, so the phenomenon will be the same. We still need B0, we still need B1, we still need to record the signal during relaxation. But we are missing one thing. Yeah, as I said, you know, these two are the same. This is a spectra of the leg. So you can see water, multiple peaks of fat, but no information on where they are. And here you've got the corresponding image, but here in the image, you know that the fat which is in the bone marrow in here is in the middle, but here the fat is everywhere. You don't know whether it's fat from the skin or fat from the bone marrow. And the water is coming from all the muscles in here. So you don't distinguish the water from this muscle and the water from this muscle. But on the image, you need to have this information. Otherwise, you go back to the spectrum in here with no localized information. And so this is what you are missing to do imaging. And so what we are missing is what we call spatial encoding. You need to get a frequency which will be selective for the type of proton, but also for the position of the proton or the water or fat. And so this is what we are going to do. So, yeah, so the basic idea is that, So as I said, the phenomenon is the same. No, physics is the same. So we still have the relationship between the frequency and the B0. But if you want to do imaging, you need to find a way to get the frequency in here related to the position of the nuclei. So you imagine that, I don't know how, but you can have, you know, water will have a frequency, a given frequency at this position, but it will have another frequency at another position, and it will have another frequency at another position. So if I'm able to do this, then okay, I record the spectra, but I know that the frequency is related to the position, so you know, with the computer I can kind of build an image. You agree with that? Yeah? Okay. So of course, people have found a way to do it. So you've got the magnet in here, and in addition, they're going to put what we call the gradient coils, and these gradient coils are going to change the frequency of the precession frequency of each nuclei specific to the localization. Okay, so let me explain to you in a very simple way. So this is a typical image sequence. Okay, we call this spin echo. So what you have in here, so the first line in here will be kind of spectroscopy, you know. You put B1, and then you wait, and you get the signal. For the imaging, what we want to do, we want to localize the information. So we're going to put on the top of the frequencies in here, we're going to put some, what we call the gradient. So gradient, as I said, is going to change the frequency, the precession frequency of the nuclei as I want. I'm going to decide that in the middle, the frequency will be 1, and on the upper left, it will be 2, and on the upper right, it will be -2. And so you've got a combination of different gradient in here. And so you are going to repeat the experiment several times. And the idea is that you are going to cover the entire image. And at the end, you can kind of reconstruct the image. But it will be the same. You need, you know, the magnetization change over time. You are going to do Fourier transformation, exactly the same. So let's, and the duration of the experiment, is not as simple as the spectroscopy, because spectroscopy, okay, you got one pulse, you wait, you record, maybe you are going to repeat this several times. And here, you are going to do the repetition time. It means that you are going to repeat the module in here several times. The number of steps of this gradient in here, plus the number of experiments, so the number of time you are going to repeat the module. So maybe you don't know, but to get an image, it can be quite fast. You know, it can be 2 minutes, 1 minute. It depends on what kind of image you want to do. So the idea is that you are going to apply this structure of different pulses and gradient so that you can cover the entire region of interest. So basically, if we go gradient by gradient, very simply, the very first one is a slice selective gradient. So we need to, so imagine we've got 3D volume. We want to just excite one slice only, okay? Not all the brain, but just near the nose, for instance, okay? So you use the gradient. So the gradient is here. So the gradient is going to change the frequency, okay? You can see that, okay, there is a decreasing gradient here. You can see that very simply, the precession frequency is going to be different for slice number 1, different for slice number 2, different for slice number 3, okay? So you create a kind of geography of the image, okay? And now you want to select only one slice. So imagine you want to select only this one, okay? You just have to choose the radio frequency, which is going to excite only this one, okay? Because you know the value of this one. And then if you apply the gradient in here, you would end up selecting only this slice in here. You don't get the signal from the other ones, okay? So once you've got the slice, you need to kind of travel within the slice to identify the lines and identify the columns. And again, you use the gradient for that. So yeah, the slice selector gradient, is quite easy to understand. You've got a gradient here, which means that the frequency will be different along the gradient in here. So if you want to take this slice, you can use this frequency. If you want to take this slice, you can use the other frequency. Okay, so you know exactly what type of frequency you need to use according to the type of slice you need to get. And in addition to that, you can also select the thickness of the slice, which we call the BW, the bandwidth. And the thickness of the slice will be depending on the slope of the gradient in here. So you can understand very easily, okay, if the slope is small, the thickness will be large. And if the slope is very high, so the thickness will be much smaller. Okay, so it's just a matter of kind of electronics. So now you've got the slice, but you need to, as I said, you need to go to the lines and you need to go to the columns. So you are going to use another gradient, which is what we call the phase encoding gradient, and you've got multiple steps of them. And the idea is, as I said, you are going to go to the lines of the slice you just selected. So again, you've got this gradient in here. It can be 0 in the middle and can be positive and negative. And you can see in here that, okay, all the lines in here have a given frequencies. And if you go to another line, the frequency is going to be different. And if you go to another line, the frequency is going to be different. And this just because of the gradient. And so again, if you want to select a specific line, so you need to use a specific frequency and you will go to the line. This is very simple, but just you to understand the basic of it. And then if you want to select the column, you're going to do the same, except that you're going to use this frequency encoded gradient, which is going to be applied along this module in here, and you are going to look at the columns in here. I don't have these. Okay, so if you combine these three gradients, you're going to get a signal which is the combination of all this information, okay? It's just that you need to understand that it's not that one signal is going to relate it to one voxel, okay? You've got the entire signal for all the voxels, but within the signal, you've got information of all the position in terms of slice, in terms of line, and in terms of column. So you need to do some post-processing, you know, and it will be, it's not going to be Fourier transformation because it is the opposite. It's going to be the inverse of the Fourier transformation because you go from the frequency to the image, okay? And so people are using this word, you know, the K-space. The K-space will be the entire signal in terms of frequencies and in terms of phase of the signals, okay? And if you have the K-space will contain all the information, and if you do a double Fourier transformation of the K-space, you should go back to the image because now you've got the information you were missing. You've got the information related to the slice, you've got the information related to the lines, and you've got the information related to the column. So in summary, you've got the information related to each voxel, okay? But this, of course, in a kind of global signal. So this is for the column. So maybe I'm not going to, yeah, this we don't care. I just want to show you, to tell you that, you know, as I said, the signal is encoded by different things: frequency, intensity, and phase. Okay, so this is what we were talking about until now. So just to show you how it can be, you know, if you start, imagine you've got a tissue, so you've got a given frequency, a given phase, and a given intensity in the frequency domain. Okay, so you start with this oscillation here in the time domain. If you change the intensity, you can see that you are going to change the overall signal coming from all the voxels in here. And you can also play with the phase, and if you change the phase, thanks to the gradient, then immediately in the time domain, you're going to have some changes in the oscillation in here. So in here, I've also changed, the phase. And if you change the phase, no, instead of going this way, you're going this way. So each time you change something, and you need to understand that these changes are related to the gradients you are using during the MRI module. And if you have multiple components, because as you know, you don't image just a bottle of water. I know. Imagine you image the brain. You've got some liquid. You've got different type of cells. You've got also fat. So you're going to have multiple frequencies. You're going to have multiple phases. So if you start from a signal here with only one component, if you add another component, you know you are going to change the chronogram in here. Again, in here, you've got the information related to all the voxels. And then if you change the phase again, you're going to change this signal in the time domain. And if you do a double inverse Fourier transformation of this, you're going to get the image. So just to finish, so this is an example of the entire K-space. So K-space, as I said to you, is not related to the image directly. It's related to the frequencies and the phases of all the voxels. So if you get this entire K-space in here, and you do the Fourier transformation, you will get the image. This is an image of a muscle. If you take the central part of the K-space, so it means that the central frequencies, if you do the same Fourier transformation, you will mainly have all the information. You know, if you compare this and this, it's not so different. And so the edges of the K-space with the high frequencies is going to give you the details of the image, like in here, but not so much. That's why, you know, some people, are trying to reduce the sampling of the case space to reduce the acquisition time. And with this, sometimes you can get as much as information as when you were covering the entire case space. But this is another story. Okay, I think I'm going to finish with this, and I'm going to thank you for your attention.